Although substitutions u equals f of x are by far the most frequently used integration method, and definitely also the most frequently used substitution method, I mean, they're so ubiquitous that sometimes you don't even realize that you're doing a substitution after you've known them well enough. There is also a substitution method where you replace x with a function of another variable. That at first seems a little bit strange, but it turns out that you can solve some really, really ugly integrals with that, and we're going to take a look at how these things work in this presentation. So, substitutions x equals h of v. Basically, some patterns in integrands would be easier if the x was actually some other function. Now that sounds just wrong, because what we would do is we would replace x with something more complicated, and that doesn't sound promising. But we've seen this in mathematics before, right? Sometimes you add 0 in the form plus minus some weird number, or you multiply by 1 by multiplying and dividing by some strange number, and all of a sudden some things just can be connected a little bit better. That basically is the spirit of these substitutions, x equals h of v. So for example, 1 minus sine squared of v is cosine squared of v, right? So a 1 minus x squared in an integrand will collapse into a single term if we do a substitution x equals sine of v, and that can help. Of course, then we have to deal with sines and cosines, but as we are going to see in our explicit example, that can be done, and in our example it still is possible to do it by hand. And in general, there are even some formulas for integrating powers of sines and cosines that can be looked up, or again, if required, could have to be memorized. I again don't think I would make you do that, but it goes with what your teacher needs to do. Okay, so typical patterns that we can attack with the substitution x equals h of v are the pattern 1 minus x squared, where you use cosine squared v plus sine squared v equals 1, and therefore you substitute x equals sine of v or x equals cosine of v. And then also the patterns x squared minus 1 and 1 plus x squared, for which you can use the fact that the hyperbolic cosine squared of v minus the hyperbolic sine squared of v is equal to 1, because then let's see, if you bring the hyperbolic sine squared over, you get hyperbolic cosine squared v is 1 plus hyperbolic sine squared v, which would apply to this pattern. And if you bring the hyperbolic sine to the right and bring the 1 over to the left, you end up with hyperbolic sine squared of v being cosine hyperbolic cosine squared of v minus 1, which would allow you to attack this pattern. Now, these two patterns are also often attacked with the tangent and the secant, because those satisfy similar trigonometric formulas. I prefer the hyperbolic cosine and the hyperbolic sine because these functions have more physical relevance than the secant function, and also because, as I often say in my classes, the secant really is not widely known outside the United States, I guess, maybe outside the English-speaking world, but it's 1 over the sine, so what's the big deal about it? Whereas the hyperbolic cosine and the hyperbolic sine have relevance in the shape of hanging chains and things like that that will be more widely known. Okay, so because this h of v usually is a trigonometric or a hyperbolic function, these kinds of substitutions are also called trigonometric and hyperbolic substitutions. And aside from solving the integrals, these substitutions provide excellent practice of working with trigonometric and hyperbolic functions. And so as we are going through this stuff, we're going to see a good number of trigonometric tricks and a nice trick of working with hyperbolic functions as we go through this. And so even though it is quote-unquote just computation, the algebra, the pattern recognition, as well as the trigonometry that we're going to take out of these computations is also valuable in itself, because the more stuff like that you can do, the less you are going to worry about ugly algebra when you're hitting an applied text. So, trigonometric substitution. Let's start with a very simple example. We want to compute the integral, the antiderivative, of 1 over square root 1 minus x squared. Now that problem looks like a joke because you already know the answer. The improper integral is the arcsine of x plus c. Let's see how a trigonometric substitution would do that. The pattern is 1 minus x squared. So if we substitute x equals sine of v, then dx dv is cosine of v, which means that the integral 1 over square root 1 minus x squared dx is the integral of 1 over square root 1 minus x is sine squared of v, x squared is sine squared of v, right? And dx is cosine v times the dv once you bring that over, so you get a cosine v dv over here. This equation, when we did the substitutions u equals f of x, we stated a specific theorem to justify it. Well, this is basically the same thing here, right? Because this is a chain rule. Basically, if you knew the antiderivative of this thing, and you plug the sine function in, then the antiderivative of this of sine of v, the derivative of that, would be exactly this, because you would get the function 1 over square root 1 minus x squared with the sine plugged in times the derivative of the sine function as the derivative. So the justification really isn't so much the clue here. The big thing is the computation and how it works. Okay, well, what do I know? I know that square root 1 minus sine squared of v is cosine of v. So I end up with an integral of 1 over cosine v times cosine v dv. That, of course, cancels. That's the integral of 1 dv. And that ends up being the integral of v, or the integral is v plus c. And as we undo things, well, if x equals sine of v, then v equals arcsine of x, and so the antiderivative is arcsine of x plus c. Now, that looks as if that might be a way to sidestep the need to memorize the derivative of the arcsine function or the antiderivative of 1 over square root 1 minus x squared. Don't use it like that. You want to know what the antiderivative of 1 over square root 1 minus x squared is without having to look it up and without having to go through this process, because as we are going to see, we're going to tackle much more complicated patterns, and then knowing certain antiderivatives can help a great deal. We will see that, I think, at the latest when we are dealing with the situation that we have integral tables or that we just are in a section where nobody tells us how to solve the integral. So do not poo-poo that memory part of integration. You also want to know the antiderivatives and the derivatives of various standard functions, and the arcsine function certainly is one of them. You want to know its derivative, and then in reverse, 1 over square root 1 minus x squared is one where you want to just have the antiderivative memorized. Now, we move on. Let's take a look at something that only looks a little bit more complicated. We want to compute the integral of 1 minus x squared quantity raised to the 3 halves. Well, same pattern, so we set x equal to the sine of v. dx dv is cosine of v. And so that means that the integral of quantity 1 minus x squared, parenthesis closes, to the 3 halves is the integral of 1 minus x is replaced with sine of v, so 1 minus sine squared of v to the 3 halves, we keep that, times dx dv is cosine v, so dx is cosine v dv here. And, well, 1 minus sine squared of v is cosine squared v. So we end up with the integral of cosine squared v to the 3 halves cosine v. That ends up being cosine cubed here, so we end up with the integral of cosine to the 4th of v dv, and now we somehow have to figure out what the integral of the 4th power of the cosine is. That doesn't sound like it's that much better than what we started with, but it's really hard to do algebra with square roots and powers and things like that once it gets a little bit more complicated than just a polynomial. And you can see this is just a little bit more complicated than a polynomial, whereas here we don't have to deal with roots and we can use some trig identities. So now we just have to keep remembering trig identities, and of course the granddaddy of all of them, as we restate what we have so far, the granddaddy of all of them is Trigonometric Pythagoras. Cosine to the 4th of v is cosine squared of v times cosine squared of v. Again, the highlighting doesn't work too well with slides generated like this, but of course cosine squared of v is 1 minus sine squared v. Alright, so that is then as we multiply out the parentheses, the integral of cosine squared v minus sine squared v times cosine squared v. And, well, the sine squared times the cosine squared, let's see, we know that the product of the sine and the cosine is 1/2 sine of twice the argument. So that means this is that we keep the cosine squared of v. Sine v cosine v is 1/2 sine 2v, and squared means we get 1/4 sine squared of 2v, just working out straight algebra. And so now the question is, what are we doing with these squares? You see, we want to get rid of the cosine squared, but we would get just more sine squareds. We want to get rid of the sine squared, and we would just get more cosine squareds. But there is something back in our minds, something about double angle identities, something way back from trigonometry. And so if you still remember that, if you remember the identity itself, great, but the least that I hope you will remember is that somehow you can express the square of the cosine in terms of sine 2x or cosine 2x. If you still remember that, you can reconstruct the rest. And so here is something where I can honestly say I don't remember the symbolic identity. What I remember are the pictures. Here's the cosine function. That's a picture that you've got to know. And if we want to look at cosine squared, well, cosine squared is just that we're squaring this thing, so that would be oscillating like this. And so here is cosine squared, and here we're seeing where previously we've got a frequency where one period is 2 pi. Now one period is pi, so that means that we have doubled the frequency factor in the argument. So a 2 definitely is in there. We just don't know whether it's sine or cosine. Well, that sort of looks more like a cosine, so it's probably going to be in terms of cosine 2x. And now we can just piece it together, because now cosine squared of x, well, let's see the amplitude here, because now it's oscillating around a height of 1/2. The amplitude is 1/2. It's no longer 1. Then it oscillates around 1/2. Well, that means it's going to be 1 plus or minus something, right? 1/2 times 1 is 1/2. So that 1/2 is our new 0 here. And now we've got a cosine of 2x, and that has to be added because the cosine of 0 is 1. So 1 plus 1 would give us 2 times 1/2 would give us the 1 here. So we have 1 plus cosine 2x, and that is the way we represent the cosine squared. Now, if we ask ourselves the same thing for the sine squared, well, again, just look at the picture. You've got to know what the sine function looks like. You square that thing, that's the sine squared function. That again has a doubled frequency, so it's going to be a 2 in there. And it still looks like a cosine. It's just that this time around it's going to be a minus cosine. So it ends up being sine squared of x being 1/2, because again, the amplitude is 1/2. The 1 just tells us that we're oscillating around y equals 1/2, and this time we subtract the cosine 2x, because at x equals 0, 1 minus 1 gives us 0, and we end up right here where we need to be. So that's the identity for the sine function. We get back to our integral. This is the kind of thing that you want to do as a side computation. This is the kind of thing that in a class I can do on a sideboard, or you just do it on another piece of paper. But what we have now is that the integral of the cosine squared would be the integral of 1 plus cosine 2v divided by 2. For the sine squared, we keep the 1/4, and we've got 1 minus cosine 2 times 2v, so cosine 4v divided by 2 dv. And, well, now we just multiply that out. So we get a 1/2. We get 1/2 cosine 2v. We get 1/8, and we get minus plus 1/8 cosine 4v. And now the neat thing is, these are things that we can quickly solve with the u substitution. In fact, that's so quick we don't even write out the u substitution anymore. Because, well, okay, before we do that, we collect terms. 1/2 minus 1/8 is 3/8. Everything else is the same. You know how that goes. You have to have good housekeeping, good bookkeeping. Just make sure everything is still there. And now, well, the antiderivative of 3/8 is 3/8 v. To integrate the cosine of 2v, we do a substitution u equals 2v. And if we work that out, we end up with du dv being 2, which means that dv is du over 2, so we get an extra 1/2. We end up with 1/4 sine 2v. Now that is something that is always hard to do in your head because it's easy to stick the 2 in the numerator rather than in the denominator and mess up that way. Remember, the one trick here is that you can always just take the derivative of what you've got real quick and see if it works out. And if you take the derivative of sine 2v, you get 2 cosine 2v, and so 2 cosine 2v times 1/4 is 1/2. So that means this part is correct. And then in the same fashion, as you integrate the cosine 4v, the antiderivative of the cosine 4v is 1/4 sine 4v, which then with the 1/8 gives you a 1/32 sine 4v here. And of course, we have the ubiquitous plus c in there also. And just like for this one also over here, if you, when you're reading a text, for example, if you're not quite sure, you can always take the derivative to make sure that this was right. Okay, so now we have our antiderivative, but the antiderivative is in terms of v. We want to have it in terms of x. Well, we know that v is going to be arcsine of x, but then these patterns here will be very, very ugly. So now we're going to use double angle identities to reduce things back to sines and cosines. So 3/8 v stays. Sine 2v is 2 sine v cosine v, and times 1/4 gives us 1/2 sine v cosine v. Sine 4v, the derivative is 2 sine 2v cosine 2v, with 1/32 gives us therefore 1/16 sine 2v cosine 2v. And that means here we've got sines and cosines, which we can replace. Here we still have double angles, but we just use the double angle identities again. So we copy the first term, we copy the second term. The only thing we have to deal with is this stuff here. Well, sine 2v is 2 sine v cosine v together with the 1/16. It gives us 1/8 sine v cosine v. Cosine 2v is cosine squared v minus sine squared v, the other double angle identity, plus c. And now, well, now we remember that, okay, now we just multiply this out a little bit more to have everything in terms of sines and cosines. So again, 3/8 v, 1/2 sine v cosine v stays. Then we've got 1/8 sine v cosine squared v gives us the cosine cubed here, and 1/8 sine v cosine v times negative sine squared v gives us the minus 1/8 sine cubed v cosine v plus c. And now we remember that x is sine v, which means that cosine of v is square root of 1 minus x squared, and that's what we have to get rid of, right? Then of course v is arcsine of x, but that's fine. But we can replace the sine with the x, the cosine with the square root of 1 minus x squared, and so what we obtain is v is arcsine x, so 3/8 v becomes 3/8 arcsine x. Sine v is x, so we get 1/2 x. Cosine v is square root 1 minus x squared, which is here. 1/8 sine v cosine cubed v becomes 1/8. Sine v is x. Cosine cubed v is square root 1 minus x squared cubed, and then square root 1 minus x squared cubed, because we've got the cube up there. And 1/8 sine cubed v cosine v, well, that's 1 minus 1/8 here. Sine cubed is x cubed. Cosine v is square root 1 minus x squared. And we've got that here, and then we've got the plus c. And, well, then, that ought to be it, right? I'm just writing it down here. That's just copying it across. Let's see, what else can we do? Yeah, we can simplify a little bit, I guess. We can write this as a 3/2 and factor a few things out. Yeah, let's see. We kept the 3/8 arcsine x. We factor out a square root 1 minus x squared. That means from the first term we keep a 1/2 x. From the second term we keep a 1/8 x square root 1 minus x squared cubed, squared, because 1 is factored out, so that's good. We can simplify that. And 1/8 x cubed is what remains of the last term here. And then, of course, the 1 minus x squared, square root 1 minus x squared squared becomes just a 1 minus x squared. And so that means, again, we copy, we do all the bookkeeping, we keep the 1/2 x, we keep the 1/8 x times 1, plus 1/8 x times negative x squared as 1/8 x cubed, and then we've got a minus 1/8 x cubed here. And that, of course, adds up together rather nicely. because now again we copy, and then we have 1/2 plus 1/8 is 5/8 x, and minus 1/8 x cubed minus 1/8 x cubed is minus 1/4 x cubed plus c. And then we simplify that just a little bit more. We're taking out, okay, we keep the front, we're taking out 1/8 x, and that means we have 1/8 x squared 1 minus x squared out front. We keep a 5 and a minus 2x squared out here, because of course 1/4 is 2/8. And well, that now is already it. So now let's check. And how do you check? Well, you check by taking the derivative, right? So we have to take the derivative of 3/8 arcsine x plus 1/8 x squared 1 minus x squared times 5 minus 2x squared plus c. First thing we're seeing here is we've got a product of three functions, x squared 1 minus x squared and this quadratic here. It's much easier to actually work things out when we have a product of two functions. So even though we just took somewhat great pains to pull it back out, we'll push the x back in. So we have that this is the same as the derivative of 3/8 arcsine x plus 1/8 square root 1 minus x squared times 5x minus 2x cubed plus c. And now we just use all the differentiation rules. So here, remember, I said you really want to know what the derivative of the arcsine is to make these kinds of double checks. So here we get 3/8 times the derivative of the arcsine, which is 1 over square root 1 minus x squared, plus 1/8 times, and now derivative of the first, this is 1 minus x squared to the 1/2, so we get 1/2 1 minus x squared to the negative 1/2, which is the square root of 1 minus x squared in the denominator, times the derivative of the inside, because it's the chain rule. That gives us a negative 2x, and then we multiply with the second term, of course, and that's the first step in the product rule. Second step in the product rule is that we copy the first term, which we're doing here, and we multiply with the derivative of the second term, which is 5 minus 6x squared, and of course the derivative of the c is 0, so that goes away. And now we have to sort terms, and let's see, we're interested in ultimately getting 1 minus x squared to the 3/2, so we'll probably factor out a square root 1 minus x squared. No, we're actually going to find common denominators here, and the first step is actually just a very quick simplification. We keep the first term, we just cancel the 2's here and put a minus sign around here, and everything else is copied. Now we factor out a 1 over square root 1 minus x squared, because that's bugging us, right? We don't want to have all those denominators. Well, we keep a 3/8 from the first. We keep a minus 1/8 x times 5x minus 2x cubed from the second. And from the third, well, in the third we essentially have expanded with square root 1 minus x squared. So we have square root 1 minus x squared squared divided by square root 1 minus x squared. The division comes out, and what remains is 1/8 times 1 minus x, square root 1 minus x squared squared, which is 1 minus x squared by itself, times 5 minus 6x squared. And now it's just a little bit of algebra. Here's what we had on the previous panel. Now we multiply out the parentheses, and well, and I took out a 1/8 first, sure, because again, that 8th is here everywhere, so we don't really want to bother with that. We keep a 3 here, we keep x times, that's multiplied out, so 5x squared minus 2x to the 4th here, and 1/8 times, well, okay, 1 times 5 is 5, 1 times negative 6x squared is negative 6x squared, minus x squared times 5 is minus 5x squared, and negative x squared times negative 6x squared is 6x to the 4th. And if we collapse all that, well, we collect terms. 3 plus 5 gives us the 8. The terms with the x squareds are negative 5x squared minus another 5x squared minus another 6x squared, so that's negative 16x to the second, x squared. And then we've got minus minus, which is plus 2x to the 4th plus 6x to the 4th. That's 8x to the 4th. And now we can see that the 8's cancel. So that gives us 1 over square root 1 minus x squared, 1 minus 2x squared plus x to the 4th, which is nothing but 1 minus x squared quantity squared. And 1 minus x squared quantity squared divided by square root 1 minus x squared is just 1 minus x squared to the 3/2, which is what we were supposed to show. All right, so this is our first integral, as you can see, there's an awful lot of really good algebra that we're practicing here. There's trigonometry that we're practicing here. Yeah, I know that's not the most fascinating thing in the world, but you want to be able to do that, because if you can do this, then there's very little else that is going to bother you terribly much as you go to applications, and you'll be able to focus on what the application does rather than what the computation requires of you. Let's take a quick break here. You may want to just go ahead and hit pause. I'm going to do that too, because I've just got to clear my throat here. Okay, we're back. So now let's take a look at another example where we want to compute the integral of a squared minus x squared to the 3/2, and that's really a prime application of these substitutions. Now, we are not going to do a substitution here, we're just going to see how an integral like this can be reduced to the trigonometric integral that we just did. So the integral of a squared minus x squared to the 3/2 dx. Well, if I factor out an a squared out of this expression, I end up with a squared times 1 minus x over a quantity squared. And if I take an a squared and raise it to 3/2, I end up with an a cubed. So all I've done here is, from here to here, I have taken the a squared out of the integrand. Alright, but now this one we know that's basically a 1 over x squared, except that we would have to do a quick u substitution. So those u substitutions certainly don't go away. So u set equal to x over a, that means that du dx is 1 over a, and that means, after bringing everything over, that dx is a times du. And so that means that our integral is just a cubed integral of 1 minus u squared now to the 3/2 times a, which is a to the 4th times the integral that we had just computed, which was 3/4 arcsine u plus 1/8 u square root 1 minus u squared 5 minus 2u squared plus c. And, well, we can now undo the substitution, right? U was x over a, so we end up with 3/8 arcsine x over a plus 1/8 x over a plus square root 1 minus x over a quantity squared, 5 minus 2 times x over a squared, and the whole thing multiplied with a to the 4th and with a plus c at the end. Okay, let's just copy that down. And now we can also multiply the a to the 4th in here, and so we get 3a to the 4th over a arcsine x over a. There's nothing else we can do with this one. But in this term, we can distribute the a's into the various summands. So let's see, we've got an a to the 4th, so we've got 4 a's. Well, one of them cancels the x over a, so that's here. That leaves us with 3 a's. If we multiply the square root with a, then of course an a on the outside becomes an a squared on the inside, so the square root becomes a squared times what's in there, which is a squared minus x squared. And we've used 1a here and 1a here. We've got an a squared left from the a to the 4th. And that a squared we can just multiply with the last term to get 5a squared minus 2x squared plus c. And that would be this integral. And if we want to check, yeah, we could do all the algebra, but let's also now move in the direction of what an advanced user does with integrals. And we're just going to look that up with an integral table. So we open the book. And of course, when I open the book, I'm by now very much locked into my book. Well, there is an integral table at the end. So let's go to that integral table. And the way integrals work, this is a bit hard to read, but they're typically sorted by integrals that involve certain terms. And we can see here there are integrals that involve square root a squared minus x squared. So let's magnify that a little bit. And let us just focus on the integrals that involve square root a squared minus x squared. That should be visible on your screen now. And as we go through that, we can see here's the integral of a squared minus x squared to the 3/2. It's claimed to be this expression down here. So now let's just go ahead and shrink that down a little bit. Pull up, pull over. Probably have to pull up a little bit more, because I want to, oh yeah, of course it's right in the middle, so it's going to be really harder to find, but we can just scroll some more here. And what do we see? The integral of a squared minus x squared to the 3/2, 3a squared over 4, 3a to the 4th over 8 times arcsine x over a. That's right here. Minus, well, the minus here is something we have to deal with. Okay, x over 8 is 1/8 x. That's okay. Square root a squared minus x squared. That's okay. 2x squared minus 5a squared. Well, that's the same with the minus sign as 5a squared minus 2x squared. So that is indeed the correct answer as long as the table is correct. And so one of the things that I can also say right here is that in some ways these substitutions were very important as long as these tables had to be computed, and then also certainly in a day and age where people may not have had these tables available. But now that tables are available, certainly this kind of stuff can be looked up. What we want to be able to do is we want to be able to do the right kinds of symbol manipulations, such as these quick substitutions that turn an x minus x divided by a into a u or so that we can read these tables and so we can follow computations where people have to do these small adjustments. As we move on, let's also take a look at how hyperbolic functions work. And so if we want to compute the integral of square root 1 plus x squared dx, well, if I set x equal to the hyperbolic sine of v, then dx dv is the hyperbolic cosine of v. And so the integral of square root 1 plus x squared ends up being the integral of the square root of 1 plus, and x squared is hyperbolic sine squared of v. Dx is, of course, hyperbolic cosine of v times dv, so that's this part back here. And, well, the square root of 1 plus hyperbolic sine squared, that is the hyperbolic cosine, and so this becomes the integral of the square of the hyperbolic cosine. Now you remember from earlier on that we then used double angle identities to do this for the trig functions. And the hyperbolic functions are a little bit nicer in the sense that we have an exponential representation. And it actually turns out, even though this is real calculus and therefore real number calculus, and so we're not going to do it here, there is a similar representation also for the trigonometric sine and cosine functions that allows a lot of verifications to be a lot simpler. So this is something that electrical engineers will see in circuit analysis, for example, or you could see it in complex analysis. But here we remember that the hyperbolic cosine is e to the v plus e to the negative v divided by 2, and then of course we have to keep the square. Well, we can multiply that out and then integrate the exponentials. That's certainly a lot easier than messing with hyperbolic identities. So the 1/2 is a 1/4, e to the v squared is e to the 2v, plus 2e to the v e to the minus v. Well, that's 2e to the 0th, which is 2, plus e to the negative v squared, which is e to the negative 2v. And if we integrate that, well, we keep the 1/4. The antiderivative of e to the 2v is 1/2 e to the 2v. Notice again how we basically, at an almost subconscious level, we're doing a u substitution here, right? This, technically speaking, whoops, I'm just not marking right here. Technically, this is a substitution u equals 2v. Well, okay, and then we get du dv equals 2, dv equals du over 2, and that's what gives us the 1/2. Or, as I said, just by differentiating, we can see that, yes, this is the antiderivative of that. The antiderivative of 2 is 2v. I don't think that requires much of a comment. And the antiderivative of e to the negative 2v is negative 1/2 e to the negative 2v. Either check by differentiation or carry out the u substitution. We get a plus c at the end, as always. And so now if you write that out, we realize that this is just 1/4 e to the 2v minus e to the negative 2v divided by 2. So that combines the last term and the first term. We've got the plus 2v here. And x was hyperbolic sine of v. So this is a hyperbolic sine. Well, that's a hyperbolic sine of 2v. So we have to deal with that a little bit. Here we would already use the inverse hyperbolic sine. But what do we know? E to the 2v is e to the v quantity squared, and e to the negative 2v is e to the negative v quantity squared. So this is a difference of two squares. So this is essentially e to the v minus e to the negative v times e to the v plus e to the negative v. And now I want to have hyperbolic sines and cosines, so I need 2's in the denominator. Well, let's see. I've got a 1/4 times a 1/2, that's a 1/8. That's a 1/2 times a 1/2 times a 1/2. So that takes care of that first term. 1/4 times 2v is 1/2 v. Then we've got the plus c there. And now this ends up being 1/2 hyperbolic sine of v, hyperbolic cosine of v, plus 1/2 v plus c. Hyperbolic cosine, of course, can be expressed in terms of the hyperbolic sine, because now we keep the 1/2, we keep the hyperbolic sine. Hyperbolic cosine of v is square root 1 plus hyperbolic sine of squared of v plus 1/2 v plus c, which we're keeping. And now we're undoing the substitution. We end up with 1/2 hyperbolic sine was x. Hyperbolic sine here was x, so we get an x squared. And if x is hyperbolic sine of v, then v is the area hyperbolic sine of x. It's the inverse hyperbolic sine of x. And if we want to check that, well, again, we could do all those derivatives, or let's just see if we can check that with a computer algebra system, and that's something that I already set up. And this is not something where I'm faking you out typing things. This is the integral that we're interested in. To convince MathCAD to compute it, we use the symbolic evaluation error, and here we are. And well, here's the result. So what do we have? We have x times square root x squared plus 1 divided by 2. That's this term here, so that's fine. Then we've got this ugly logarithmic term, and it turns out that this is the logarithmic representation of the inverse hyperbolic sine. So when you're dealing with these integrals, you often either end up with inverse hyperbolic functions, or you end up with certain logarithmic representations. Either way, you don't want to be surprised by those things. It turns out that this is actually correct. Okay, so that was our hyperbolic substitution, and so we're already with concluding notes here. For the integrals of products of powers of sines and cosines, as well as of hyperbolic sines and cosines, there are reduction formulas. So that means even though these substitutions will always end up ultimately with these ugly products of powers, these things actually can be handled. Well, these formulas, however, can be found in tables. Yes, you can prove them, you can derive them, but ultimately, at least personally, this is something that I look up in tables. If you have a test where your teacher says you need to have them memorized, memorize them. There's nothing wrong with knowing something. But ultimately, I can also say that tables are a topic of another presentation, because really what's left for us to do now is to put it all together, to just put ourselves in the situation where somebody says, here's an integral, deal with it, and we're going to talk about how we're choosing which integration method to use, and then also how we would use an integral table and how we would use a computer algebra system in such a situation. That being the case, I'll see you for that presentation. Bye. Oh, come on.